centripetal force, or we looked at centripetal acceleration. You know, once the centripetal acceleration brings about the centripetal force, and we came to the realization that whenever a body is moving at a constant velocity or constant speed, because the direction of the body continues to change, there are different velocities at every point, at any 2 points of the body. And due to this changing, due to the changing direction, which brings about the change in velocity. So a change in velocity is caused by the changing direction. And whenever there is a changing direction, change in velocity within a given time, there is acceleration. We determine the direction of this acceleration and realize that this acceleration, which we gave the name centripetal acceleration, is directed towards the center. And so the name centripetal acceleration or radial acceleration. Okay. So because every acceleration from Newton's second law is caused by an external force, we determine that force or this external force which causes the centripetal acceleration. And then we had the centripetal force given by the relation, F is equal to mv squared over r, where m is the mass of the body, v is that constant speed, and then r is the radius of the circle. Then we also derived a relation for centripetal acceleration given by v squared on r, where v is the constant speed, r is the radius. We further used the relationship between linear acceleration, linear velocity, and an angular velocity to further break this down. We used it. So either you substitute into this or this, and we have m omega squared r. This also becomes omega squared r. We use this when the body moves at a uniform angular velocity. And so when a body moves at a uniform angular velocity omega, we can determine the period, which is the time taken for the body to make a complete revolution. We can also determine the frequency and use this information to find the number of complete cycles and so on and so forth. So that is a quick review of whatever we went through last time. Today we are going to build on where we ended last time. Before that, let me quickly drop attendance on the platform. Okay, very, very necessary. So give me a minute or two to quickly produce assignment, the attendance for today. So I'll be updating it as at when others join. In our last session, we were connecting situations of circular motion and then what provides the centripetal force. So we looked at when a car negotiating a bend, or a curve will stay within the circular path due to centripetal force. And we realize that this centripetal force, which keeps a car within the circular bend or the oval, is provided by the frictional force between the tire and the road. So we equate centripetal force mv squared on r to frictional force. Please, how do we express frictional force? Mathematically, how do we express frictional force? Class, anybody to help me here? Mathematically, how do we express frictional force? Anybody to help? Yes, Amma. Mathematically, how do we express frictional force?
M mass times acceleration.
Amma, frictional force. Oh. Frictional force. Frictional force is directly proportional to what? To what? I think we've gone through this. Oh, Charlotte, Equia and Co. Frictional force is directly proportional to
the net force.
the normal reaction. So we said F is directly proportional to the normal reaction R, or other books represent this by N. And so F is equal to a constant of proportionality R. F therefore is equal to, this constant of proportionality is what we call as the coefficient of static friction, mu. But because when a body lies flat on a surface, its weight, mg, is balanced by the normal reaction R. R is equal to the weight of the object, mg. Therefore, frictional force is given by mu mg. This is the expression for frictional force when the body lies flat on a surface. Okay, so we equate the centripetal force to the frictional force between the tire and then the road, which is mu mg. Okay, let's take it contextual so you follow. When a car negotiates a bend or a curve, when a car negotiates a bend or a curve, the centripetal force is the centripetal force that keeps the car within the circular path. It's equal to the frictional force between the road surface and the tire, the vehicle tire. Therefore, mv squared over r is the centripetal force, and we are equating it to friction. So if mv squared over r equals frictional force, then this is mass of the body. This is also the mass of the body. So we have v squared over r equal to mu g. Therefore, v is equal to mu rg taking the square root. This value of v, okay, gives us the maximum speed. Maximum speed a car can possibly move with at a radius r and coefficient of friction mu. What we can deduce here is that for a car moving on a flat road, flat curvy road, and this is very, very important, flat curvy road, because it changes if the road is not flat, which we'll look at. For a car moving on a flat curvy road, its maximum velocity or the surface velocity should be any value which is less or equal to square root of mu rg. So to safely, okay, stay within the circular path, the maximum velocity depends on this, and it should be any value which is equal to this or less than. The moment v is greater than this, the car skids off. So if v is greater than root of mu rg, the car skids off the road. Skids off the road. And so this gives us an expression of maximum speed. So we can deduce that the maximum speed depends on one, v is directly proportional to square root of the coefficient of static friction. V is also directly proportional to the square root of the radius. As for gravity G, so long as it's a constant, so long as we find ourselves on the surface of the earth, okay, and this value mu is the nature of the road. So coefficient of static friction mu determines or instead of using the defines the nature of the road. So mu defines the nature of the road. Now we all know that if the road is so rough, okay, value of mu, in fact, mu lies between 0 and 1. If a road surface is so rough, then mu is anything close to 1. If the road is so rough, okay, and if the road is so smooth, then mu is close to 0. So the value of mu determines whether the road is smooth or rough, okay? And because maximum speed, can I flip the screen?
Yes, please.
Because maximum speed depends on mu, which is the nature of the surface. This is the reason why Road Safety Commission advised that whenever on rainy days, drivers must decrease speed. Okay, because mu depends on the nature of the, and whenever it rains, okay, the rain fills those tiny pores or holes on the surface of the road. So the road becomes so slippery or yes, smooth. And so the road becoming so smooth means that the value of mu is something close to, okay, 0. And so if you are driving and you don't control your speed because this has decreased, okay, it can be, the consequence can be so fatal. So this is the reason why Road Safety Commission advised that we reduce speed whenever it rains, because the rainy situation drops the value of mu. That is the practical application of this. Please, are we okay, class?
Yes, please.
So V defines the maximum speed, and it depends on mu and R. Okay, here to R, when you are driving and the road is so small, it means the radius, look at these two circles. There's a center. When the radius is small, it means because V is directly proportional to square root of R, it means V2 must be small. When the radius is large or greater, then it means V can also be a bit greater. So the velocity, the maximum safest velocity depends on the radius of the road as well. Okay, so it means for two different values of mu and V, that for two different values of mu, there can be different values for V. When the road is dry, for dry road, you have this directly proportional to square root of mu when it's dry. And when the road is wet, you also have coefficient, okay, of friction when the road is wet. So it means for two different conditions, there can be different values of mu and V. Dry road and wet road. So note this carefully. I'll be giving you questions, okay, on application of this. All right. So this is an application of centripetal force whenever a car negotiates a bend. Another application, please, if you have any question, ask. If you have any question, quickly ask. Nakuya ama a Chrysler na if you have any question, ask. Carl. So another application of centripetal force is this. When an object is tied to a stone, or when a string is tied to an object and weld, okay, the object could stay within the circular path due to centripetal force. So an object tied to a string and weld, there is application of centripetal force here. And here, the centripetal force that keeps the object within the circular path is provided by the tension in the string. And this is the reason why when an object is tied to a string and being welded, the moment there is a break in the string, the object falls away or skids somewhere. It fails to stay within the circular path, meaning the centripetal force which keeps the object within the circular path is provided by the tension within the string. So the moment the tension is not there, the object fails to stay within that circular path. And here, the radius is equal to the length of the string. Last time I demonstrated that assuming this is from my hand to where the object is, okay, is the length of the string. When this object moves in a circular pattern, you realize that the length of the string is equal to the radius of the circle. The radius of the circle. All right, so as we move on, we'll be looking at different applications of centripetal force and what to do. Let's quickly apply this in solving a question. All right, I'm giving you a question. A 1,500. Let me take a shot as well and then drop it on the platform. Okay, so the question is sent to the platform. A 1,500 car moving on a flat horizontal road. Moving on a flat horizontal road. Negotiates a curve. Negotiates a curve. If the radius of the curve is 35 meters, if the radius of the curve is 35 meters, and the coefficient of static friction between the ties and the dry pavement is 0.500. 0.500. Find the maximum speed the car can have and still turn successfully. Find the maximum speed the car can have and still turn successfully. Okay, so let's give it a try. Whilst I look for another question for us to try our hands. Let's discuss the first one I gave to you. All right, so at a 1,500 car moving on a horizontal road. So the mass of the car is 1,500 kg. And negotiate a curve. If the radius of the curve is 35 meter, and the coefficient of starter friction is, so mu is 0.500. Calculate the maximum speed. So if you want to go start from the foundation, then when a car is negotiating a bend, the centripetal force mv squared on r is equal to the frictional force between the road and the car. Okay, and this is mu mg. The masses would cancel. Then you have the velocity being equal to the square root of mu rg. Okay, and this is the expression of maximum velocity. It must be any value which is less or equal to this. Now, what is mu? Mu is 0.5 on 10 times the radius is 35. Gravity, let's use our usual value. Once it's not given to us, let's use 10. Okay. Therefore, you have root of 35. This is 5. Okay. Then 15. So 7. And what's the square root of 175? What's the square root?
7.
Come again.
5, 7.
Which must be 10 or 11, which is which?
13.23.
Oh, okay. It's one or more than 144. So
13.23.
So this must be the maximum speed which the car can move with and turn successfully. Meaning the driver must not speed anything more than this. It should, the speed must be less than this or equal to this. Anything greater than this, the driver will just skip off the circular path. That is the meaning of maximum safest speed. The value must be anything less or equal. The moment it goes beyond this, there's trouble. Please, are we okay? And I'm sure all of us got this.
Yes, sir.
None of you got it wrong. Abba, Johannes.
Yes.
Sir, please, I was having network problems, so I wasn't able to join early. So I did understand the explanation at the beginning. When I came where you had the question.
Abba, don't worry. I'll give you the video, okay?
Yes, sir.
I'll video you. So just pay attention from here, right? Okay, let's
Right.
also look at the question I just sent to
Sir,
you. Hello.
I don't understand how the in the question was like the dry pavement is 0.500.
Mm-hmm. And that's the roughness level of the road or of the pavement. So I said that the coefficient of static friction describes how smooth or rough the surface is. Whenever you walk on well-polished floor, okay, the floor being so smooth and well-polished means that friction coefficient of friction of the surface is very, very low. And when it is low, if you are not careful, you can easily slip and fall. So the value of mu lies between 0 and 1.
1.
If the surface is so rough, the value is close to 1. If it's so smooth, then almost 0. Okay. So mu
Okay.
describes the nature, how rough or smooth the surface is.
Okay.
All right. So please, 3 minutes. Let's attempt this question I just typed on the platform. An object of mass 50 kg moves around a circle of radius 6.0 meter with a constant speed of 10 meter per second. Calculate I, the angular velocity, and I, the centripetal force. 3 minutes, and it's 3:42. 3:42. I want to update the record of attendance. An object of mass 50 kg moves, so the mass is given 50 kg, moves around a circle of radius 6. With a constant speed of 10 meter per second. Ten 10.0. Calculate the angular velocity. So angular velocity relates to linear velocity, or that's linear speed by v is equal to omega r. So omega, therefore, would be equal to v on r. V 10, r 50 kilogram. Therefore, we have 0.2 radian per second. And here, I'm sure somebody's worry is that, say, this is meter per second. This is,
Yeah.
hello, hello.
Please, R6.
Ah, hey, so now you can see mistakes. Good. Hey, you are doing well, oh, Charlotte. So 10 on 6, and this is 1 point, remember 4.
6, 7.
6, 7
6-7
radian per
meter per
second.
second.
I'm sure somebody's worry is that we said, yeah, this is in meter per second, this is in meter. How can we change this to have radian per second? That is not your worry. What must actually be of worry to you is that all the actors and then the actresses in this movie of Omega, this must be changed to SI unit, meter per second, and this must also be in SI meter. And once this actor and the actress are in SI unit, Omega would also be in SI units. Okay. So the next question is about centripetal force. F is equal to mv squared on r, which is also equal to m omega squared on r. Both must work. If you use first one, 50 by 10 squared over 6 must be equal to 50 by 1.67 squared times 6. You must have the same value for them. Let somebody confirm.
$833.33.
For both.
I only did for the first part.
Are we there?
The second part, I got 836.67.
Do you know why? Divide, Charlotte, divide 10 by 6.
Yes,
Is it exact? 10 divided by 6. Is it exact as 1.67?
no, you get 1.6666666666.
So the drop or that change is due to how you approximated this. All right. So the next question is for you to just try later and then report to me. All right. So
Yes.
let's look at another aspect of simple circular motion, which we call as conical pendulum. Conical pendulum. Conical pendulum. Conical pendulum. Conical pendulum. What is conical pendulum? Okay, a quick demonstration. When a body is being in circular motion and it is flat, here the body moves in such a way that it's as if the string makes an angle of 0 with the horizontal. So flat, when it's flat, it's like this. You whirl it or revolve this object in such a way that the string makes an angle of 0 to the horizontal, meaning it's flat. Okay. Now for conical pendulum, this is the string, the vertical string. It is held so that as the body revolves, it makes a certain angle with the imaginary vertical. So assuming this short ruler represents that vertical, I tilt the string so that it makes a certain angle theta with this. So as the body revolves, there is an angle theta the string makes with the vertical. So the revolution is like this. So there is an imaginary vertical, which is the marker, and as the body revolves, that angle is maintained. That angle is maintained. Okay. In drawing, the point of support, my hand. This is the string, the imaginary vertical line. Now, the string is made to make a certain angle theta with that vertical, whether at this side or this side. And this is the object. Okay. Now, because the string makes an angle with the vertical, it looks as if as the body object rotates, the string cuts the shape of a cone. The body goes through the circular base, and then the string cuts the shape of a cone. Please, can you see? Can you
Yes,
see the shape of the cone being cut by the string?
Yes, please.
Okay. So, as the body revolves, this is the circular base produced by the body. And this remains the shape of the cone cut by the string. The reason for which we have conical pendulum. Conical pendulum. Please say it after me. Conical pendulum. From your homes.
conical pendulum.
Again.
Conical
Again.
pendulum.
Yaba, you didn't say it. Yaba.
Pendulum.
Pendulum.
Okay.
Conical pendulum.
The boys are quiet.
Conical pendulum.
So this is the radius of the circle. Now, this is the weight of the object, mg. There is a certain tension holding the object to the fixed points. So the tension is always directed to the fixed point. Now, if I extrapolate this weight vector, I have this angle here alternating with what is here. So if this is theta, this is also theta. Now, we have the tension vector. We have the tension vector being inclined at this angle theta. So let's resolve this into the tension into 8 components. So it's like having this tension T making an angle theta. And we want to resolve the tension into 8 vertical components and 8 horizontal components to obey the triangle law of vectors. So what will be the vertical component? What will be the horizontal component? Yes. What will be the vertical component? What will be the horizontal component? Somebody to help me get.
Sir, please, I want to try.
Okay.
So the vertical component to be Ty and the horizontal will be Tx.
I get what you are saying, but that is not the final value. So this is Tx, but Ty represents Y for vertical, and Tx meaning the horizontal of this T. What will be the expression for Ty and Tx? Okay, I think Yaba wants to also try.
Please, Ty will be T sin theta.
Okay, so if Yaba is right, but let's go through it step by step. So when we take sine of this angle, sine theta is opposite, which is Ty, divided by the hypotenuse, which is T. Therefore, Ty is T sine theta. Then, Carl, your hand was up. Help us obtain expression for Tx.
So the expression is T cos theta.
Good. So this is T cos theta. Okay. So this side remains the horizontal component. And then, so this will be T cos theta. And then the opposite, instead of bringing it here, let's bring it along the radius. This is T sine theta. But the question to the house is that by bringing it along the radius, does it make sense? By bringing T sine theta along the radius, does it make sense to you?
Yes, please.
Yes, please.
I'll ask why. So why? Why does it make sense to you? Because ideally it's supposed to be the opposite, which is here. But we are not writing it here, by bringing it along the radius. Why does it make sense to you?
Because they're equal.
Pardon?
Because they're equal.
You are not polishing it so well. Though you have the idea, but it's not well polished. What is the reason behind bringing it here? And
Equal vector approach.
and no. The equal vector. Vectors are equal irrespective of where they are. If they have the same what? If they have the same
Magnitude and direction.
magnitude, direction, and
Equal.
parallel.
Yeah.
You've talked about they have the same magnitude, meaning they are equal in magnitude, the same direction, and they must be parallel wherever they are. So this is the reason why we are bringing it, moving it from here to here. Abba, is that okay? Carl and Herbert
Yes.
and Tucci. Okay. Now, when we look at vertical equilibrium on the object, for vertical equilibrium, on the object, we can see that T cos theta is balanced by the weight mg. Then for horizontal equilibrium, you realize that the T sine theta is unbalanced. So this component has no balancer at the opposite end. But because you see, T sine theta is directed along the radius towards the center. Because T sine theta is directed along the radius towards the center, we conclude that then the T sine theta must be equal to something. Yes, who can tell us? Judging from the direction of T sine theta, though it's unbalanced, but we can draw the conclusion that then T sine theta is equal to,
Frictional force.
come again,
Centripetal force.
centripetal force. Because centripetal force is directed along the radius towards the center. So we equate T sine theta to mv squared over r. Equation 2. So by dividing equation 2 by equation 1, dividing equation 2 by 1, we have T sine theta over T cos theta equal to mv squared over r times mg. Please, if you take your time systematically to divide mv squared over r by mg, you end up having this. This will be equal to mv squared over r times 1 over mg. So it becomes mv squared over rmg. That's what I've done. So the masses cancels out, the tension cancels out, and you have sine theta over cos theta equal to tan theta being equal to v squared over rg. When you make v squared a subject, you have rg times tan theta. Therefore, v is also equal to rg times tan theta. And this also gives us the expression for the maximum speed of a conical pendulum. V max for a conical pendulum. Meaning that for a conical pendulum, its maximum velocity, V max, is directly proportional to, similar to flat road, is directly proportional to the radius of the road. Sorry, I said road. The radius of the circle. And V max is also directly proportional to the square root of the tangent of the angle of tilt, theta. So when you vary R, it affects the maximum speed of a conical pendulum. When you vary theta, it also affects the maximum speed. So it also means that for a conical pendulum, its maximum speed must be any value which is less or equal to root of Rg times that. Now, one helping equation, I'll call it auxiliary equation to this one, is that, look at the diagram. If you eliminate the tension in the string, you see that this length represents the length of the string, and this length also represents the radius of the circle. And so when you take the sine of this angle, sine theta, sine theta is equal to the opposite, which is R, over the length of the string L. And so from this, we can deduce that then the radius of the string is equal to L sine theta for a conical pendulum. So if you don't know the radius and you have the length of the string and the angle, you can use this relation to determine the radius. So R is equal to L sine of theta. So this is a helping equation which enables us to find the radius R of the string in case it is not given and L and theta are provided. Please, are we following?
Yes, please.
Yes, please.
Insura Badampa. Oh, she's not here. Ah, okay. Then request a song for three friends of yours. If you are here. So look at something. This is a revolving conical pendulum. So long as I try to maintain the angular, keep the angular velocity to be constant, things I can derive from it is that I can determine the time taken for this to make one complete revolution. If I determine t, I can find a frequency, okay, and then can also tell the number of complete revolutions this body makes within a time t. All right. So to obtain that, are you done writing what is here?
Yes, please.
No, please.
Oh, I've cleared half. Amma.
Sir, I want to ask a question.
Okay.
Sir, please, after you spoke of the formula for a car negotiating a bank, you spoke of an object tied to a string, and you wrote that centripetal force is equal to tension in the string.
Yeah.
Then you said something like R was equal to L. Please,
Yeah.
what did you mean by that?
I meant that R is equal to L. Amma, that's what I meant. Okay,
But sir,
please. Uh-huh.
if you think R equal to L sine theta.
There are conditions, okay, on which each one, this one and the previous one works. The first one I was talking about when we have flat or horizontal movement of objects. When an object is whirled and the nature of the whirling is flat. Flat. This is what I said. This is the object, the spring. Then from my hand to where the object is the length of the string. Now, if the object is in circular motion, we are looking at this object being whirled flat, meaning it should make an angle of 0 degrees with the horizontal. So as if I'm whirling it on the board, the angle it makes, okay, with the surface of the board is 0. That is what I mean by flat revolution. So when the object is revolved or is in revolution and it makes an angle of 0, the string makes an angle of 0 with the horizontal. This is what I mean by flat revolution. An object tied to a string and whirled, where the revolution is flat. So in this case, you realize that the radius of the circle is equal to the length of this string. Here, it is not flat. This is another horizontal revolution, just as the flat one. But here, the string makes an angle of theta degrees with the vertical, the imaginary vertical. So, they don't apply under the same principle. One, the string makes an angle 0 with the horizontal. This one, the string makes an angle theta with the vertical. Are you okay?
Yes, please. Thanks.
It's a very important question. So under flat horizontal revolution or cycling, the string makes an angle of 0 degrees with angle of 0 degree with the horizontal. That is where we are saying that the radius is therefore equal to the length of the string. But on a conical pendulum, this vertical makes an angle of theta. All right. Okay, so if this body moves at a uniform or constant angular velocity or angular speed omega, then you see, we said let t cos theta, but t cos theta is balanced by mg. Then T sine theta is equal to the centripetal force. But here, because we have omega being constant, centripetal force will be m omega squared r. So when we divide equation 2 by 1, we have T sine theta over T cos theta equal to m omega squared r over mg. We still have tan theta, but this is equal to omega squared r over g. Ishra, help me make omega squared a subject. Ishra, bow down, can help me make omega squared a subject.
Please, I'm coming.
Okay. Ishra, you done?
Yes. Tan theta over
Okay, all over
all
r.
over
R. Thank you. Now, omega therefore is equal to
omega therefore is equal to
Mr. Yeah,
hello, Amma.
your voice was echoing.
Pardon?
It's better now.
Okay. So the omega is equal to the square root of J on R times tan theta. Okay. Last, we have derived a relationship between omega period. Yes. So what is omega in terms of period? What is omega in terms of period? Yes, class.
What is
Omega in terms
omega
of
in
period?
terms of period?
Hey,
Sir, please,
pardon?
I do not understand.
Mute yourself.
Mute yourself.
Oh, we derive a
We
relationship
derive a
between
relationship between
omega and T.
omega and T.
Yes.
That's what I'm
That's
looking
what
for.
I'm looking for.
Okay, Samuela.
Okay, Samuela.
Sir, omega is equal to 2 pi on T, capital T.
Thank you. So we have omega being equal to 2 pi on T. So this is G on R times. Therefore, if you are looking for T, all that has to be done is make T the subject. Okay. Before we make T the subject, we want to simplify this one. You see, tan theta is equal to sine theta over cos theta. So in place of tan, we want to substitute sine over cos. So sine theta over cos theta. Then we've also had R being equal to L sine theta. So we also substitute that for R, L sine theta. And then simplify. So we have root of, under the root, J sine theta cos theta times 1 over L sine theta. And we have sine theta canceling sine theta. The final results we'll have is equal to J over L cos theta. Okay. So by that simplification, we clear all this and put J over L cos theta. So 2 pi over T is equal to this. I want somebody up, okay, make T the subject. Let's make T the subject from what we have here. Let's make T the subject. Everybody should try it. When you are ready, you share it with us. From what we have here, make T the subject. If you are ready, you share yours with us. Okay, Chrysler, T is equal to
T is equal to root of bracket 2 pi squared L cos theta over G.
did you say 2 pi squared, Chrysler?
Yes.
No, Chrysler, something is missing. Okay, Herbert, what have you also had?
So I got T is equal to 2 the root of J over L cos theta.
Come again. T is equal to
2 pi over the root of J over L cos theta.
okay. Something is missing. The final response. Something is missing. Let me pick Yaba.
T is equal to 2 pi square root of L over G cos theta.
L over G
Cos theta.
But the L, okay. All right. This is how I'll do it. I'm looking for
eating
T.
the food.
Amma and go mute
I'm
yourself.
going to throw it away. That's it.
Herbert, you are
Yes.
feeding us with every information you are churning out. So mute yourself. This is how I will do it. In mathematics, when you reciprocate one side, you do the same to both sides. You see, what I have at the right-hand side is the same as root of J over root of L cos theta. So this is the same as this. Yaba, your hand is still up. Or it's a mistake?
Yes.
Okay. So if I reciprocate this side, then I must do the same thing to the other side of the equation. So if I have T over 2 pi. Then the other side must also be root of L cos theta over root of J. So once I want to make T the subject, it's more or less like multiplying 2 by 2 pi, or letting this multiply this. I'll have T being equal to 2 pi times, then I bring all of them under the common umbrella. 2 pi times L cos theta over J. And I'm done. Yes, some of you were saying this, but I just wanted to reshape what you were saying. So this then becomes the formula for the period. It isn't a formula, because the point is that if you are looking for the period, once you find root of J over R times tan theta, you can, if you get a number for it, you can easily find period out of this when you understand omega is 2 pi over T. But we just want to polish it to look so nice. The reason for which we have derived this relation. Okay. So the period, therefore, from this becomes 2 pi times square root of the length of the string and the cosine of the angle of tilt divided by gravity. Okay. Can we determine frequency from here? Frequency. All right, Abba.
Please, the frequency will be 1 on 2 pi square root of J over L cos theta.
Thank you. So it would invert. Okay, so 1 on 2 pi times J on L cos theta. Okay, then you can also be asked, in case we had a certain number of revolutions, calculate when L, theta, and all that is given. Calculate the time taken to make a certain number of complete revolutions. So here we are looking for small t. Okay, this is how you, when you are given that number of revolutions, you can determine t. You see, period is equal to total time over number of revolutions. So in place of this, substitute big T for T over N. So this will be equal to 2 pi times root of L cos theta over J, and make small t the subject. Small t, therefore, is equal to 2 pi times N times L cos theta over G. So with this, if you are given the number of revolutions, the length of the string, and then the angle of tilt, you can determine the total time taken for a certain number of complete revolution. Yes. All right. So any question? So when there is uniform angular velocity omega, this is what you can derive or deduce from it. Let's apply this in solving a question. How we can use conical pendulum concepts to solve a problem. Agreeadom, are you there? Okay. All right. Class, are you ready? I'm giving you a problem. An object of mass 10 kg is whirled round An object of mass 10 kg is whirled round a horizontal circle of radius 4 meter. By a revolving string. Inclined to the vertical. By a revolving string inclined to the vertical. If the uniform speed of the object is 5 meters per second, if the uniform speed of the object is 5 meters per second, calculate I. The angle of inclination of the string to the vertical. Calculate I, the angle of inclination of the string to the vertical.
Sir, please, you said if the uniform speed is
If the uniform speed of the object is 5 meters per second, calculate I, the angle of inclination of the string to the vertical. And II, the tension in the string. The tension in the string. Take gravity to be 10 meters per second. The tension in the string. Take gravity to be 10 meters per second. So, how many minutes do I give you to try this? Call your, hello.
Please, you said an object of mass 10 kilogram is rolled round a horizontal circle of radius
4 meters by a revolving string. By a revolving string inclined to the vertical.
Okay, thank you so much.
Okay. And so how many minutes do I give you to try? Oh, call your own time to, you won't call. Okay. 4 minutes. And it is 4:36. So 4:40, I'm coming to you. Enjoy. Problem of the day. Yeah, but what did you make for theta?
I got 31.96 degrees.
Approximately 32.
Yes, please.
Who else had another a different answer? Or if you had the same, let me know. If you had the same answer, let me see you.
So I had the same answer.
Who is talking? Samuela. Okay. It's true. That is it. So, how do you obtain that? We are given V, R, and G. And maximum speed is given by square root of Rj times tan theta. So this is given 5. So it means 5 squared equals 4 by 10 times tan theta. Therefore, tan theta equals 25 on 40 aka 5 on 8. So theta therefore is equal to the tan inverse of 5 on 8. And that must give you 32, approximately 32 degrees. Then the second question. If you are through with the second question, share with us what you had for the tension in a string. Yes. Whoever is through with the second part of the question. Samuela.
Sir, please, I have 62.5.
62.5. What's the unit? Samuela,
Newton.
and when you call values, add the unit. Who else had a different value? Yaba.
I had 117.92 newtons.
117. Okay, so we have two different answers. Is there any third answer? Okay, let's see if any of these two given answers is right. So, with the tension, I can use two different equations. We have T cos theta is equal to mg, and we also have T sine theta equal to mv squared on r. Any of these two equations can be used to determine T. Let's use one and see. Once we have theta, T cos of 32 is equal to 10 by 10. Therefore, we have T equal to 100 divided by cos of 32. And what is 100 divided by cos 32? Those of you with calculators, please call it out for me. 100 divided by cos 32.
117.91.
117.91.
Yes, sir.
Then let's call it 117.9 approximately. If we use equation 2, we also have T sine of 32 giving us 10 by 5 squared over the radius, which is 4. So we have 5 on 2 by 25. Give me 5 on 2 on 25. So 125, right? 125 divided by 2.
62.5.
Charlotte again. 62.5.
Yes, please.
You were running with it, Charlotte. And this is equal to Charlotte, this is equal to
That's 117.94, 2.9.
so everywhere you go, you are connected. Please, any question? No question. Okay. So what I'm going to do is that I'm going to send you 2 questions on conical pendulum as your assignment. In fact, this week, let me promise you something. I'll be giving you a lot of questions. I spared you in our Friday's meeting. I didn't engage you. Okay. So I'm going to give you questions which you have to submit today. And then there will be another section which I would also send from tomorrow. So I'm sending you 2 questions on conical pendulum. Do it and then send it to me on your various platforms. Please, if you haven't formed one, do so, because I'll be marking through it. Okay. All
Okay,
right.
sir.
Okay.
Sir, please, we should submit it before we time.
Oh, this is the deadline for this particular one is tomorrow.
Oh, okay.
Okay. Because right after tomorrow,
Okay.
I'll send you another set to work on.
Set, okay.
Okay.
Okay,
So this
sir.
is where I draw the curtains on today's meeting. Okay. I'm going to send you your work set to work on. Okay. All right. Until then, take care of yourselves and bye-bye.
Bye.
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 Okay. Yeah.